Hello, and thank you for taking time out of your busy schedule to join us today. My name is Dr. David Bleiweiss, Chief Medical Officer for Cell Science Systems. The purpose of this webinar series is to broaden your understanding of the immunological differences between innate and specific immunity and how those differences manifest in disorders ranging from gluten and other food sensitivities to more severe manifestations such as celiac disease. In this lecture entitled Zonulin, Intestinal Permeability, and Immune-Mediated Disorders, Facts and Fantasies, Dr. Alessio Fasano, Chief of the Division of Pediatric Gastroenterology and Nutrition for Massachusetts General Hospital and Director of the Center for Celiac Research, will be discussing his research into zonulin, intestinal permeability, and immune-mediated disorders. Be sure to stick around at the end of the lecture, as I'll be giving you information on some of Cell Science Systems' innovative laboratory testing.
Nevertheless, to say that I feel so inadequate compared to Dave. He got such cool videos. Where is he? Dave, where you got those? Well, anyhow. So, YouTube. No, that's not cool. We're gonna do something. All right. So, by the way, how much time do I have? It's an hour what? No, we're not gonna go 2 hours because otherwise you guys kill me. So also because this is such a controversial issue that I would like to leave us a little bit more time for discussion because I'm pretty sure that there is a lot of stuff that we can discuss about this issue of leaky gut. As a matter of fact, this is an interesting topic, if you wish, because it's been a black box and it still is. For many, many years, because there are lots of misunderstanding, there are very few facts, a lot of fantasies, and what I want to do in the next hour and a half, let's put it this way, is really to be factual and tell you what we know about, the situation in leaky gut. And again, it's an interesting story if you're interested in how stuff works and how we stumble upon it in the entire business of understanding a little bit more the situation. The reality of the story, and this is the objective, is that, again, if you allow me to be a little bit philosophical here, we are whatever we are because we are really the quintessential of this interplay between what Mother Nature decides to put together as a project, i.e. genetically speaking, what we are, and the environment that surrounds us. It doesn't come as a surprise that if you take identical twins, so genetically identical, and you split them at birth, one of these kids is, raised, on the North Pole, and the other one is raised in Africa, at the end of the day, they will be very two different individuals. The way that I would like to conceptualize, if you allow me to, my Italian nature has to surface here and there. It's like to have a wonderful, superb marble block, like Michelangelo was given by the Medici in Florence. The marble block is just amorph. It doesn't tell you anything. It depends on who really work on this marble block, the sculpture, what you're going to have out of there. And if you visit, Florence, and you had a chance to see not the fake, David outside, but the one that's really in the Uffizi, it's astonishing. And, again, Michelangelo got the chance to work with this marble block when he was 19, a kid. And this marble block was sitting there for 50, 60 years because there was a lot of discussion how precious, how beautiful marble block, and they didn't want to screw it up and give this, task to people that would not do the job right. And the year will come, this young kid come across and say, I know what is in there. I can pull it out. Give me the chance, and you will see something astonishing. And, you know, to get out of the metaphor, the marble block is our genetic makeup. Michelangelo was the environment that curved out of the marble block. That's beautiful statue. So the question is, how this interplay between genes and environment will translate in what we are actually as human beings. And, you know, now if we want to be factual and molecular and mechanistic, the question is how the genes that are within our body will interact with the environment that is outside our body so that we become whatever we are. Because under normal circumstances, this interplay cannot happen because there are very tightly controlled, regulated barriers that separate the environment outside of our body to our inside, our genes. But if we need to interact, there must be some way, some pathways, some shortcuts that these, you know, two different worlds can find themselves. Now, here comes the biased view of this process, because as a gastroenterologist, I really do believe that the largest interface where this interaction occurs is the guts, are the guts. And the reason why, we'll see in a moment, there are all the, you know, the anatomical, functional, and, objective, findings that seems to suggest that that is the case. Typically, as we know in terms of, the physiological, path, when you push physiology to the limits, you move from health to disease. So this interaction with the environment most likely is also at the heart and soul of problem that deals with inflammation and autoimmunity. And the question is how we can connect all these dots of our genes, the environment. We discussed a little bit about the microbiome, that is a third key element in this interplay, the battlefield that will eventually get to the clinical outcome so that we can be in a state of health or to lose that state of health and switch to disease. That brings me to the concept of the intestinal tract and this superbly sophisticated and unbelievable organ. Now, when I teach functional system, in general, there's this misconception that the intestinal tract is not a big deal. They are much more noble and sophisticated organs. And I have also always an argument with my colleagues. And, because after all, what is the intestine? It's a long tube that makes this magic change from, put one thing on the top, that's food, and got something at the bottom that is poop. That's it. And it's much more than that. And typically, when I talk about how important is this organ, and we discussed so many times during this day and a half that it's not just impinged on GI function, but the function in the entire body, I make a quick statement and a survey with my students that if you allow me, I will do the same over here. Because again, my colleague neurologists say that the brain is the most important organ in our body. The cardiologists say that is the heart. The pulmonologists say that are the lungs, and so on and so forth. So let me ask you this. How many of you guys ever had a stroke? How many of you guys ever has a heart attack? Just one, okay. How many of you guys have ever had an episode of pneumonia? How many of you guys have ever had an episode of diarrhea? Did I make my point? But the question is, how you define the gastrointestinal tract? Because any kind of definition is quite reductive for what we're going to discuss today. The best, and I believe the most comprehensive, definition I got came from one of my students. I teach also elementary school. forget the spelling here. The intestine is a long tube with a clean opening on the top and a dirty opening on the bottom. Appreciate the quintessential here. What are you asking for? What is going on? I heard some fish. Yeah. I asked her, and she said, this is the noise that my dad makes from the dirty ants. So, you can imagine his face when I met him. But anyhow, you know, what is so important about the intestine and why we have to spend time to discuss the matter if this is really goes way beyond the gastrointestinal diseases and so on and so forth? Well, the father, all physicians already appreciate that the intestine was the crossroad of all human diseases. And this is, again, his statement, all disease begins in the gut. And this was a long time ago. I told what I reviewed here, that the gut is not like Las Vegas, and I showed you yesterday, you know, the reason why. What happened in the gut does not stay in the gut, but today we're going to go a little bit more in depth about that. The reality of the story is that the intestinal mucosa is truly the battlefields where friends and foes need to be recognized every day, 100 times of the day. And this because will give you the balance between tolerance, i.e. state of health, or immune response, i.e. inflammation, therefore a state of disease. And imagine, again, let's go back about this, you know, gene-environment interaction. This is the largest port of entry of environmental factors that can dictate this balance, this yin and yang. Now, if you shrink yourself millions of times and put yourself on these battlefields, you will see quite a challenging environment. Hundreds of craps a day comes through. Some are good friends, nutrients, for example. Some are definitely enemies, like pathogens that can really harm us. And the intestine has to really decide many, many times a day who is friend that should stay there and who is a foe that needs to get out of there. Just as a comparison, the second largest interface that is, the lung. The lung has a very monotone function. Everything that goes through needs to get out of there. And that's important for their pollens, bacteria, viruses, particles. They don't need to stay there. The skin, the third largest interface with the environment. Not one, we have 7 layers to make sure that nothing comes through. The intestine can't do that because otherwise we'll be out of business in a blink of an eye. So I appreciated the sophistication of the decision-making process that the intestine has to go every single day. And it's mesmerized to me that despite this complexity, mistakes are rarely made. But what are made, we pay a dear price. And for example, celiac disease that we briefly mentioned yesterday is the ideal paradigm to understand how we make these mistakes. Because a friend, a nutrient, a protein that comes from food will become a foe. So this is the classical example of this decision-making that goes bad, that goes in the wrong direction. Now, I'm assuming that you're not going to see anything here, but when I said anatomy, functional mechanism suggests that the intestine is much more sophisticated and complex than we previously appreciate. I really mean it. This is a cross-section of the gut with the lumen being here and the body over here. And these are color-coded, cells. They are part of this meshwork of mechanistic and very sophisticated interacting, cells that makes this decision-making possible every day. Starting from the inner lumen, this red, stuff here is this layer of a single layer of cells, the epithelial cells, that is pretty much what defend us against this uncontrolled passage of crap from the environment. Single layer cells, single layer. And again, going back to the comparison that I told you yesterday, it's like the walls of a middle-aged city that, you know, it surrounds the city so that we are defended by this, you know, uncontrolled, you know, entrance of enemies. Immediately underneath, you have these green cells. These are immunological cells called dendritic cells. These are pretty much the avant-post soldiers that are able not only to defend us, but to have an understanding of what is going on in here. They already have sort of periscopes that they bring out and see into the lumen and say, who is here? And based on what they scoop, they prepare the rest of the army for peace or war. Now, also here, extremely abundant in blue, are other immune cells. They are the B cells, the one that they have the best capability of weaponry, i.e. producing antibodies, including IgA antibodies that can be secreted within the lumen with special tricks. That's the reason why I call secreted IgA. And finally, the T cells, the ones that when they go wacko, they really go big time. The ones that have the most powerful weaponry, these are the ones that, for example, destroy the intestinal celiac disease autoimmune process. But look how they are all arranged. And this really speaks volumes. Where is the function of not only surveillance, but interact with the environment? Because these soldiers are not there just to fight. They are there also to understand and eventually write treaties, peace treaties with the enemy if it's necessary. And again, I don't have the time, nor I have the, the possibility to go in deep details, but the beauty of all this done, it's mind-blowing, because this single epithelial cell layer not only is a wall, a morph, they have antennas, they have sensors that technically we call pattern recognition receptors that you heard about, the toll-like receptor and so on and so forth, that will understand who is here. Not only that, but if this pattern recognition receptor, they feel danger because there is an enemy that they know that can give trouble to us, will already communicate underneath with these old soldiers that say, guess what, guys? Into lumen, not now. There is somebody that can eventually give us trouble. Get ready. Get prepared. What kind of language they use? Secreting specific chemokines. They are chemicals that attract these soldiers on the battlefields. And this is done regularly every day. Every day. And keep in mind that this crosstalk eventually leads to the decision, do we need to keep these folks out? And eventually going after them, or we need to bring them in because we need them here for whatever reason. And that's what the essence of antigen trafficking that is so important in this interaction between genes and environment, because without this trafficking of antigens, we would not be whatever we are. The genes, epigenetics, and the state of health and so on and so forth would be totally impossible. Do you appreciate, guys, the beauty of nature in doing all this? This is absolutely mind-blowing to me. Now, I told you that when you push physiology to the extreme, you spill into pathology. And we discussed yesterday about celiac disease as a paradigm of autoimmune diseases. We also mentioned that the recipe for autoimmunity, until the recent past, called for two ingredients: genes, many, because these are multifactorial diseases, not a single gene disease like cystic fibrosis, thalassemia, and the environmental triggers are known most of the time. For celiac disease, we know that's gluten. That is the one that triggers the entire business. The third element that makes this holy trinity that was not clear until the recent past was the breach of these single layer cells. In other words, a leaky gut. They allowed these enemies to come through and eventually instigate the autoimmune process in people that are genetically skewed to develop autoimmunity. And this brings me to the leaky gut. Facts and fantasies. Now, again, there are very few facts. There are many fantasies. And that's the reason why this term, leaky gut, particularly among traditional medicine folks, it really gives the bumps. In a sense, they say, gee, this is so creepy and not cool because this has been totally vilified. And there is no evidence that this is true, is real, that can do anything, exists, and so on and so forth. And again, as usual, guys, there is no black and white in life. There are no people that are right and people that are wrong. There is always the compromised gray, because that's pretty much what is coming out for what we understand about this leaky gut situation. So what are the facts? The facts is, again, that this intestine is a very long tube. In adult, it's roughly 15, 20 feet long. The facts are that this tube is covered by single-layer cells, as I told you. In the past, the single-layer cells was conceptualized as a floor in which each cell is the tile, and the space in between cells is completely sealed with a grout, cement. So all this interface with the environment, this exchange information was supposed to happen through the cell and not in between the cell, because that space in between the cell was completely and totally sealed. Now, if you take the intestine of an adult and stretch this intestine, because it is a tube of 20 feet long, but again, has valleys and hills. They are called folds. And then if you zoom in, there are these finger-like protrusions that I showed you yesterday, the villi, and each cell, the core of the intestine, is not smooth, but it has little bumps on the top. They're called microvilli. So if you take the entire surface and you stretch it out, we're talking about a double tennis court. 3,000 square feet of interface with the environment. So imagine how much stuff is going on a daily basis. Imagine how much stuff is going on. Not only that, and again, I don't want to go too much in details, but it's important to appreciate the dynamic nature of this single layer of cells that cover the intestine. So shrink again yourself 1,000,000 times and put yourself in there. Now, these valleys in between these villi, they are called crypts. In there are the stem cells. This is one of the few places in which stem cells are active from birth to death. No matter how old are you, your guts are 5 to 7 days old. That's the life of an enterocyte, i.e. an epithelial cells that cover the intestine. Why we waste all this energy? Why we waste all this effort to change the cells all the time? Guess what? That's a really harsh environment. And you can't afford a mistake, because if you are bombarded by chemicals, radiation, heat, toxins, so that you have genetic modifications, so in other words, that these cells can go through genetic mutations, and they don't work the way they're supposed to, we will be in deep doo-doo. And nature can't afford that. Not only that, the other thing that is mind-blowing to me is these cells, they go through a process of maturation that reminds me very much the story of the caterpillar or the butterfly. Very sad story. When they are immature, they're down there, they are really ugly. They are really unsophisticated. They are very rudimental. They are not able to do too much. In other words, they look like a worm. Then a biological clock will tell this rudimental cell that it's time to mature. And when that information is passed to the cell from the valley, i.e. the crypt, start to migrate along the villus. And during this process of migration, during this trip from the bottom to the top, start to change and mature in one of the most sophisticated, complex cells that we have in our body, to become a mature enterocyte with all this machinery to digest and absorb the foodstuff, these antennas to see enemies, the capability to have immune function, the capability to talk with the neighboring cells, the capability to interact with the nervous system and endocrine system, a wonderful butterfly. Guess what, though? When they reach that level of sophistication, their life is few hours, after which they fell off in the intestine, like butterflies. And all this is because we really want to make sure that our intestines are cored by the most efficient, sophisticated, active cells with no chance that they are mutated in their function. And again, when I say function, I don't mean just digestive stuff, but all the sophistication I was telling you before. Until the 80s, this concept that these cells were linked to each other by a grout was a dogma. Until a Japanese group in the late 80s said, wait a second, this space in between cells is not sealed. There is no cement. There is not a wall. Rather, there are doors, most of the time closed, that technically are called tight junctions. So with the door concept is also implicit the concept that sometimes this door that can be open and create a shortcut from stuff in the environment to come through in our body. Now, until then, the major headaches for people that were interested in immunology, particularly autoimmune disease, was how instigator autoimmunity, that in general proteins, can get into our body. Because one thing is for sure, guys, and this is something that never changed in the past 60 years, proteins, they don't go through cells. It's like to pretend that 2 dozens of elephants will go through a wooden needle. It does not happen. Because proteins, they love water, so hydrophilic. The cell wall, it's very hydrophobic, and there is no way that proteins can come through. They are huge. So there was always this headache, how did it happen? How this interaction with the environment happened? How this trafficking happened? The answer was, we don't know, but we know that happened, and that sufficed, and that's it. Now, with this finding that we have doors, there was a complete, shift of paradigm. I said, well, if there are doors, they may open once in a while. Maybe this is the path through which these enemies, i.e. instigators of inflammation, can come through. But the question was, if there are doors, where is the key? How these doors are modulated? Who decides if and when they are open? And for almost another 2 decades, we have no freaking clue about this until we stumble upon this mechanism that led to the discovery of Zonulin. Now, I was privileged to get an award, a Paul Willing Award, not long ago. And I, in my typical style, I decided rather to say, gee, the discovery of Zonulin, it turns to be a big deal. It was act of a smart thinking that I was so cool that I thought about it, and I went after it, and I discovered it. That is bull poop, because the vast majority of discoveries are made by serendipity. That, by the way, is my favorite English word. Let's be frank. The English vocabulary is totally unsophisticated. It's made by, 600, 700,000 words? That's all. Italian vocabulary is made by almost 2 million words. That's the reason why we Italians, when we talk, we go on and on and on. We use our hands and so on and so on. You got to use the entire vocabulary. But it's one word that I can't give rights. How can I really express in Italian the quintessential content of serendipity? The unforeseen that is there. Something that is lined up and is meant to be. There is no way that I can translate this. And this is a story of serendipity that I think that I want to share with you, since I have 2 hours to fill, so I can do that. The real deal, how this started, was that when long minutes ago, I went to Maryland. I was very much interested in diarrheal diseases. Remember, I'm a pediatric gastroenterologist, and the ones that I really was working on very hard, because it was claiming many millions of lives, was cholera. Very bad disease, even now, claims millions of lives, particularly in kids in third world country. And again, the long story short is that I had put on a task to develop a vaccine for cholera. At that time, we knew that there was only one major weapon the cholera was making, that is called cholera toxin, an extremely powerful toxin. And therefore, I engineered this vaccine by taking the genes of cholera toxin out, leaving everything behind, with the idea that this vaccine would not induce disease, but would induce an immune response that would protect these kids. It did everything under the sun, at the level of the bacteria, at the level of the animal studies, everything worked great, and therefore we were ready to go prime time for clinical trials. Now, when we talk about clinical trials, and we're talking about, early 90s, and we're talking about vaccines, we need volunteers. And guess where volunteers came from? Where? No. Even in the 90s, they won't make too much money at that time. We were medical students, not prisoners, because the Belmont, law banned to use prisoners. Medical students. For $250, that's not a negligible amount of money. These students were recruited, and they were given 3 options. Option number 1, placebo. You drink water, so you're going to be fine, and you got $250 for nothing. Option number 2, you got this vaccine that we know is safe, and therefore you got, again, $250 for nothing. Third option, you got the real deal. You got cholera, but we'll take care of you. So, well, many kids sign up because 2 out of 3 said, what a big deal. Well, actually, it turned to be not 2 out of 3, but only 1 out of 3 because the vaccine sucks. In other words, sure, the vaccine didn't give the 40 liters of diarrhea that the kids that got the real cholera went through. But still, 3-4 liters of diarrhea that made that unacceptable. And when you fail like that, entire generations of, workers and investigators are burned on these, situations. And, the most logical thing to do is just to give up and say, forget it. And that's exactly what I did for 2-3 days. I got drunk. I was very depressed, literally 2 years of work in the toilets. That was it. But then we went to the drawing board and tried to figure out, long story short, we end up to discover a second toxin outside the cholera toxin that was making these people sick by opening these gates. Never described before. And this toxin turns to be the reason why these folks had the residual diarrhea. And then when studied the mechanism of this toxin, we realized it was way too complicated, that Mother Nature did all this machinery just to be the target of a toxin that, by the way, makes us sick. So reasoning that probably cholera, being a smart fellow, was mimicking something that we make, we went after the counterpart of this toxin, and that's how we discovered Zonulin. At that time, we had no clue what kind of Pandora box we opened. As a matter of fact, I believe this is one of the most fascinating stories that have been involved in terms of what we learned from there. First of all, we learned that, again, it's useless to go through all the details, but what we learned is that, again, these black lines here turns to be pretty much what we were looking for. This is a serum of people that had a high level of zonulin. We, in the meantime, developed a test to measure zonulin in the blood, in the lab, and so on and so forth. But we still didn't know what kind of molecule we were dealing with. And finally, one of my students was able to come up with a sequence of this protein, and turns to be that zonulin is the precursor of this molecule here that is called aptoglobin 2. Aptoglobin is a very ancient protein that, most of you guys probably don't even know. But the old doctors, when we didn't have the SED rate, the CRP, used aptoglobin as a biomarker of inflammation. It comes in 2 flavors, aptoglobin 1, the ones that we know very well, that is, with us for living, is a scavenger of hemoglobin. So in other words, when there is hemolysis, intravascular hemolysis, this guy will capture, eliminate hemoglobin, so to avoid oxidative stress of the tissue that can be destroyed that way. So it goes vis-a-vis with inflammation and comes as a pre-protein, single peptide, then it's cleaved here in two subunits, beta and alpha. Much later, as you see in a moment, came this second, variant of aptoglobin that's called aptoglobin 2. Same story, comes in a single, protein that is cleaved into the cell. And again, these two subunits, the beta subunit is identical to the aptoglobin 1. The alpha subunit is the two copies of the alpha 1 because it's the duplication that I will tell you in a moment about. And therefore, people, they can have three possible arrangements. You can be homozygous for aptoglobin 2. You have two copies of this guy here, that is this one here. You can be homozygous for aptoglobin 1, so you have two copies of this guy here. Or you can be heterozygous, so you can have a copy of this, and that's what you see here. It turns to be that zonulin is this guy here that you can barely see, that is the precursor of aptoglobin 2 or pre-aptoglobin 2. Totally unexpected because, we didn't know. This protein does different stuff for a living. It turns to be in its immature pre-aptoglobin form, losing peptide junction, and when it's mature, does something else. How is it released? That's something else that's also very cool. I showed you yesterday those two peptides from gliadin that can release zonulin. How they do that? They do by interacting with this receptor, one of this pattern recognition receptor that I was telling you in enterocytes, that is called CXCR3 receptor. This is a receptor that was described a long time ago, in general present on immune cells like T lymphocytes and B and NK cells, but now we know they are produced by also enterocytes. And I think that is very interesting, at least to me, that this receptor has been implicated as target to impeding T cells mediated destruction in autoimmune diseases like MS and type 1 diabetes, described a long time ago. And again, you see here that when you take epithelial cells, that you see here, you see in red decoration with the cytoskeleton and in blue the nucleus, and you expose these cells, this either gliadin or bacteria, they are the two strongest stimuli to release zonulin. You see zonulin is produced and packed in these blobs here that are green and released right away. But if you use casein, for example, that does not happen. So it's specific gliadin and specific those two peptides to interact with this receptor and release zonulin. And once it's released, zonulin, communicate with the enterocytes to say, look, you have a gate with your neighbor cells. I want that gate open, and does this through a very complex, pathway that involves the receptor of epidermal growth factor. And again, it's not worthwhile to go in details. It suffices to say that the steps are, there are instigators, including gliadin and bacteria, that release zonulin through the CXCR3 receptor. Once zonulin is released, we interact with this receptor and we communicate to the cell, please open that gate. And all this happened in a very short period of time, 20 minutes or so. I'll show you yesterday this picture again, just to reiterate the concept that, again, you can go from closed gate to open gate in a very short period of time due to this release of zonulin that is CXCR3 mediated. Now, mainly because it cost me 3 months, $500 to do the slides, I want to show it. This is as much as we understand about how zonulin communicate the cells to open these gates. So whatever releases zonulin really activated intracellular cascade of events. They are very complex. It suffices to say that these tight junctions, these gates, are made by a complex number of proteins. So they are, the ones that interact with each other and interact with similar protein in the neighbor cells. This is a space in between cells that, again, in the past were thought to be totally sealed. And once zonulin comes in, you have rearrangements of these proteins that will be released from this, edge of the cell, will leak into the cytoplasm of the cell. So you have a situation from gate close to gate open in a very short period of time. In general, it takes 20, 30 minutes. And again, this is in a Fritz fracture. So if you see the lateral side of the cell, these are, the macrovilli, the surface of the enterocyte, the face of the lumen. This is the cytoplasm. This meshwork here represents the tight junction. The more complex, the closer are. And if you have zonal release, you go from closed to open in a very short period of time. Now, when the stimulus, gliadin, bacteria, whatever, is removed, everything goes back to the baseline in a very, very short period of time. Genetics. This is another cool part of the story. And again, we had no clue what we stumbled upon. Evolutionarily speaking, haptoglobin is a very ancient protein. Came into the picture roughly 450 million years ago. Soon after that, the fish split from the rest of the animal kingdom. So fish, they don't make haptoglobin. But the one that we're interested in, zonulin, it came much, much later, 2 million years ago. 500,000 years after that, we split from our cousins chimpanzees, meaning that zonulin is made only by human beings. No other animals, they make zonulin, at least as form of pre-haptoglobin 2. They make zonulin-like proteins, but not exactly the ones that are in humans. By the way, again, this is something that I do quite often. Any idea how many autoimmune diseases, afflicts humankind? A little bit more than 60. Roughly 75, 80. How many autoimmune disease these guys are experiencing? Right? 0. Chimpanzees, they don't have autoimmune diseases. So it's quite interesting that zonulin turns to be one of the 400 genes that differ between the two. The gene of zonulin sits on this very interesting chromosome, that is chromosome 16, a tiny chromosome that accounts for roughly 5% of the human genome, but on which there are genes that have been located. They are very important for many, many diseases, particularly autoimmune disease, cancer, and disease of the nervous system. Among autoimmune diseases, the genes, for example, for lupus and type 1 rheumatoid arthritis sit on chromosome 16. Cancer, acute non-lymphocytic leukemia, breast cancer, lymphoma, and myeloleukemia, and prostate cancer sit over there. And this is the one that, I don't know, I'm not an expert, but my dear colleague then, he knows much better than I do about disease of the nervous system, Lou Gehrig's disease, leukodystrophy, MS, and autism genes are sitting over there. When zonulin was discovered and cloned, many investigators worldwide went through the same process and asked, which diseases this gene is related to. And they came up with the same 3 categories. Autoimmune disease, including ankylosing spondylitis, celiac disease, Crohn's, rheumatoid arthritis, lupus, and type 1. Cancer, breast cancer, lung adenocarcinoma, and so on and so forth. The disease of the nervous system, chronic, including MS and schizophrenia. Among the cancer, what really captured my attention is the glioma. And again, the reason why it did is because, again, you heard about this issue that there is a gut-brain axis all the time. And controlling the gut permeability has a similar mechanism that controls the blood-brain barrier. And these are a couple of papers that just were published on the role of zonulin in control of the gut-brain barrier in a situation of glioma. This group published this from Germany, published this in 2009, so already 4 years ago. And what they show pretty much is that zonulin, that is the stuff in green, that is very close to the perivascular, part of the blood-brain barrier and of the glioma, and therefore in the blood-brain barrier, seems to be upregulated in gliomas. And the more severe is the glioma, the more zonulin is produced, the more breach of the blood-brain barrier occurs. So they use the zonulin expression as a biomarker severity of the glioma. Just published 2 months ago is this other paper, talk about the transmigration on neural stem cells across the blood-brain barrier induced by glioma cells. You heard yesterday that the brain has the capability to have stem cells. They're now not completely gone. They're under specific circumstances they can be revitalized to do stuff. Now, these folks were able to show through cell lines and animal models that zonulin is present in these specific glioma cells, and when it's released, pretty much what they do, they pretty much increase the permeability of the blood-brain barrier that is measured by this parameter called transepithelial electrical resistance. So the lower it is, the more open are the tight junctions, the leakier is the blood-brain barrier. And they also were able, by injecting these cells into the systemic circulation of mice, to see that these cells will eventually get to the brain by crossing the blood-brain barrier and reach the intracerebral gliomas. And you see here the staining in blue. I don't know how much you can see, but you see this is a cross-section. This is a cross-section of vessel. You see the circle, and this is the sagittal section, along the long axis section of a vessel, of a capillary, the blood-brain barrier. So it looks like really that, that's the scheme that they came with. So if this is the blood flow and this is the brain, and these are the tight junctions that control the blood-brain barrier, what they conceptualized that the astrocytes and the gliomas will eventually, on this other side, the glioma cells, will release zonulin, will make this to leak and allow the cells and other stuff to come through. That is pretty much the heart and soul of the problem that you have in brain tumors. Again, just think about this. Half an hour ago, maybe 20 minutes ago, I told you how the story started. If when I failed this issue with the color vaccine, somebody would tell me that this will be coming across, I would say, you must be out of your mind. What are you talking about? It was totally unpredictable. Now again, going back to the genotype of zonulin, alias optoglobin, I told you that comes in three different possible arrangements of genotype. Homozygous for optoglobin 1, meaning that you do not produce zonulin. Heterozygous, meaning that you have one copy of the zonulin gene, or homozygous, they have two copies of the zonulin gene. Now, this is the comparison of several autoimmune diseases, celiac disease, Crohn's, schizophrenia, and chronic kidney diseases. Just look at just for a second the black column here. We're talking about the distribution of these three different haplotypes, arrangements, genotypes, in a normal population. These are done in different continents, so there is a little bit of difference among the different groups. But the bottom line is that roughly between 10 and 20% of the human population worldwide do not produce zonulin. Roughly half of the population, 46%, they produce one copy, and the remaining, 30–40%, they produce two copies. Now look at the red column. These are the people that are affected by specific autoimmune disease like celiac, Crohn's, schizophrenia, chronic kidney disease. You have a dramatic reduction of the representation of the people that do not produce zonulin, that goes down 2–3 times, and it's counterbalanced by the increase of the one that have two copies, meaning that people without immunity are skewed compared to the general population in terms of zonulin gene presence and number of copies. And now, it looks like, by several studies, that the more copies of zonulin you have, the more severe is the disease. If you're homozygous with zonulin and you come down with an autoimmune disease, your mortality rate is twice as much compared to one copy, and or of course, zero copy, you don't develop the disease. So that is pretty much what has been described so far. And here is another example of zonulin in inflammatory bowel disease. So these are people that have Crohn's disease on this drug that is a non-steroidal anti-inflammatory drug, and you see the amount of zonulin there. These are in remission. These are the ones that are on the drug, but they are not got in remission, so the zonulin is not coming down. And these are the ones that are not treated at all, and you see the highest level of zonulin in the serum of these people with Crohn's disease. Now, I told you that zonulin is specific of humans, so animals, including mice, they don't make zonulin. But you can manipulate the genome of mice by introducing the zonulin gene. So this is the normal mouse. How cute is that? That of course they have only the alpha-1 chain, so they only have the haptoglobin 1. This is a transgenic mouse in which we introduce one copy of the zonulin gene, and this is another one in which we introduce two copies. So this guy does not make, haptoglobin 1, but mimic, the folks, the human folks, that have two copies of the zonulin genes. And when you put these animals under stress, specifically you treat this animal with a chemical to make their intestine to inflame, and you look at their small and large intestine, you see that compared to normal mice, the damage when you expose these animals to these chemicals is much more severe. So you look at the colon of these animals compared to this one that is a normal mouse, not zonulin, and this is the untreated. The entire colon mucosa is gone, completely wiped out. I see this kind of damage only in animals that are radiated, like that they are exposed to radiation, like that they are, in Chernobyl kind of situation. So it's that severe. So this brings now to the point, is this leaky gut an epiphenomenon, just associated with this condition, or integral part of how we got sick? So there are a lot now of evidence that this tight junction dysfunction, alias leaky gut, are involved in a series of problems, with some bacterial toxins that can make this intestine to leak, ischemic reperfusion injury. This would take a total different lecture here that is extremely interesting. Many drugs, not only non-steroidal anti-inflammatory drugs, but many other drugs, and alcohol can make your intestine leak, and infections, including bacterial and viral infections, can eventually make this leak. But I want to finish up by really focusing on the autoimmune disorders and what is the meaning of the association with leaky gut and autoimmune diseases. So what are, the evidence right now, going back to zonulin, of dysfunction of this tight junction, meaning that you produce too much zonulin, and therefore you open the shortcuts for too long that can create this massive uncontrolled passage on non-self antigen that can instigate inflammation and eventually autoimmunity in people that are genetically skewed to develop autoimmunity. I told about gliadin, I told you the mechanism, but the second mechanism that we found that is undisputable is SIBO, small intestinal bacterial overgrowth or proximal bowel contamination. That's the second strongest, actually, it's stronger than the gliadin business in releasing zonulin and making the intestine leak. These are some experiments that we've done a while ago, published a while ago, in which pretty much you see uninfected cells compared to infected cells, the release of zonulin that increase, and the change in permeability that increase when these cells are contaminated with bacteria, and you see that this huge drop in resistance. That means huge increase in permeability compared to the untreated animals. And when you block this pathway, because we have now way to do that, i.e. that you can use a synthetic peptide that blocks zonulin, you pretty much revert the situation. This is under control, meaning that this drop in permeability is totally zonulin independent. What kind of disease we're talking about? Well, there are many now that at least anecdotally have been described to have a leaky gut. And again, we don't know if there is a cause-effect relationship or it's just an epiphenomenon. And again, it's not just autoimmune diseases. Look at this: MS, stroke, schizophrenia, asthma, COPD, ARDS, dilated cardiomyopathy, and I can go on and on and on, until you reach tumors and metastatic diseases. So there is a lot that is now accumulating into the literature describing this breach of the intestinal barrier, but with no clear understanding which one is the chicken and which one is the egg. Now, again, we had an in-house ELISA to measure zonulin in the blood of people. And here we compare two populations, two autoimmune diseases, celiac disease and type 1 diabetes, in which we test the zonulin levels in patients. Look at the number. This is not a really small number, 190 patients here, 340 here. And you see the level of zonulin levels much higher than the controls that are below this line here. Interestingly enough, family members, first-degree family members, also they have a slight increase in zonulin compared to controls, but lower than the patient's counterparts. Meaning that if the zonulin-dependent breach of intestinal barrier is important for the pathogenesis of autoimmune diseases like celiac disease, type 1 diabetes, is necessary but not sufficient. And now we know why. Because when you breach the barrier and stuff comes through, the destiny, as I mentioned you before, depends who you are. If you have an immune system that is functioning correctly, the immune system would take care of that, and we would not even know that happened. But if we have an immune system that is skewed toward food allergy, toward cancer, toward autoimmune diseases, then that uncontrolled passage of antigen can put us over the edge and create the problem. So, I think that contrary to what was 10 years ago, there is a general agreement, the recipe of autoimmunity called for these three ingredients: genes, environment, and this dysfunctional intestinal barrier that allows these two physically to interact. If this is true, it's also true that you take any of the three elements out of there and you can stop or prevent autoimmunity. Eliminate the genes is a no proposition. There are too many. We don't know for most of the autoimmune disease what genes are we talking about, so that's not a proposition. Eliminate the environmental trigger autoimmunity is a proposition that's valid and available only for celiac disease, because we don't know what makes people sick with MS, rheumatoid arthritis. So what about, eliminating this third element? Because that was the key passage to prove that this is not an epiphenomenon, but is an integral part of the pathogenesis of autoimmunity. And that's where we developed this synthetic peptide that I was mentioning you before, that the way that works binds to this EGFR receptor, but does not communicate to the cell to open the gate. So when the real deal, i.e. zonulin, comes, it cannot communicate to the cell to open these tight junctions. And what I will show you is a proven concept that zonulin inflammation and autoimmune pathogenesis in animal models and specifically in type 1 diabetes and acute lung injury. This rat model, it's a rat model of diabetes that's very, very close to the real deal, i.e. diabetes in humans. These are animals that develop diabetes around age 60, 65 days, that is the corresponding of age 30, 40 in humans, and they are insulin dependent. So if you don't give insulin to these animals, they die because hyperglycemia. So what you see on the left is one of these animals this is a group of animals that develop diabetes, and there are two parameters that we follow here. One, the permeability of the gut in magenta, and the other one, the serum glucose in blue. This is when these animals are weaned. So in other words, food is introduced. So they are breastfed by their moms until age 20, 25, and then food is introduced. At the time of food introduction, the intestinal permeability is normal, glucose level is normal. After roughly 1 or 2 weeks they introduce baby food, they start to leak. This is the normal threshold of permeability of the gut, and you see this cross the line. But the glucose level is still normal. After 1 more week, they start to produce autoantibodies, the one that attack the islets that produce insulin. Still no diabetes. It's only after 2-3 weeks that all this happens, leaky gut and autoimmune production of antibodies, that they start to lose tolerance of glucose, and eventually they develop diabetes. So it looks like that the leaky gut precedes the onset of the glucose intolerance. Now, the same animals that were given on a drinking water this blocker, you see that the permeability did not change and the glucose level stayed normal. So this was the first time that we proved that this leaky gut is not an epiphenomenon, but an integral part of the pathogenesis of autoimmunity. And when we look at the islets, i.e. where insulin is produced, and we do the immunostaining, we had the confirmation that we did the trick. So these on the top are the islets of animals that developed diabetes that were untreated. So the islets are like a balloon in which the air, the content of this balloon, is made by these beta cells that produce insulin, and the wall of the balloon is made by these cells that produce glucagon. So in animals that they develop diabetes, it's like that you punch the balloon that is deflated. So the air, i.e. the insulin-making beta cells, are gone. As a matter of fact, you don't see anything here. While if you stain for glucagon, you see the balloon deflated, that it's collapsed on itself. And that's the classical picture of a pancreas of a diabetic individual, animal or humans, doesn't matter. The same animals that were treated with zonulin inhibitor, you see that the air, insulin-producing cells, are still there, and of course the glucagon, cell-producing cells, are still at the edge of the balloon. So this is a preserved islet compared to a destroyed islet. So now this shows mechanistically that indeed the prevention of diabetes in these animals was due to the protection of these islets. Why? Because this uncontrolled instigator, we don't know what, that was coming through, that instigated immune cells to produce an attack against these beta cells, was prevented. Another disease, quite interesting, that again was totally unpredictable, is the acute lung injury. It was already known that you develop acute lung injury, for example, also in the COPD and so on and so forth, due to the breach of the barrier of the epithelium of the airways. And there is an animal model in which you can do that, in which these animals are treated in a certain way. So they go from this lung permeability that is very low to this lung permeability that is in black, that's very high. And if you block this process by giving increasing amount of zonulin blocker, you see that this comes down, gradually. And again, this, you see this also in terms of, different ways that you do this, subcutaneous versus, local. So in other words, that you put this in the airways, and this is the activity in terms of inflammation that comes down, the cytokines that come down, and so on and so forth. And if you look at the staining of the lung of these animals, this is a control animal. This is an animal that goes through the process of lung injury because of this process that is artificially done. And this is the animals in which zonulin was blocked, and looks much more close to this than this. So even acute lung injury seems that the zonulin process is important. So I'm going to go straight to this. This is in humans now. And you see that, this is the lactulose-mannitol ratio, i.e. the gut permeability of individuals who are controlled versus asthma. So the people with asthma, they have a leaky gut. And you see now that zonulin in the blood of these folks controls compared to the asthma people that goes up. Interesting enough, even if you have allergy, multiple food allergies, the zonulin levels are up, very similar to the guys with asthma. So let me wrap it up with there are so many studies in animal model that doesn't translate in humans. So is this applied to humans as well? 45 minutes, so I'm going to slow down. Again, I will take another 20 minutes or so that you guys, we can chat or go on lunch earlier. It's a beautiful day outside. I don't think that I have to spend too much time to listen. This is self-explanatory here. I've been showing this forever. I still don't understand it. But anyhow, these are all the steps that we now know they are involved in the pathogenesis of celiac disease. And again, one, you eat gluten. Two, you have this leaky gut. 3, gluten comes through and is deamidated and therefore will interact with the dendritic cells that will present this to mature dendritic cells to immune cells. And these immune cells, because they are genetically skewed, rather than to get rid of the enemy, will start to produce chemokines. They are very offensive, i.e. they will kill cells because they are TNF-alpha interferon gamma. and destroy the intestine. This leads to the autoimmune process. Then there are the B cells that produce other antibodies, including the TTG antibodies that we use for diagnostic, and maybe they also have a role in this auto-destruction. So theoretically, any of the 10 points that are outlined yellow here could be a point of attack to stop this process. What we do right now, we are here. We do not eat gluten, so that all the other steps cannot happen, and definitely it's the best way to go. The question is, if we go to step number 2, i.e. we stop this process, are we going to do the same? We're going to obtain the same results, i.e. prevent all the downstream process. So in other words, if we block this gut permeability with the zonulin inhibitor, can we do that? Now, this is probably the longest clinical trials of alternative treatment to the gluten-free diet that is out there. Started in 2006, almost 800 people have been through these trials. And the bottom line is, in terms of safety of this molecule, this zonulin inhibitor is a pussycat. It doesn't do anything, though that's good news. Now, the very first trial that we did was a single-dose, double-blind, placebo-controlled trial. So you have now people with celiac disease on a gluten-free diet, so they are in remission, and they eventually, blindly, either they got gluten alone, knowing that this will give them trouble, or gluten plus the zonulin inhibitor. The one that got gluten alone, they got an increase of permeability of the gut that, interestingly enough, this was a single dose of gluten, so in other words, a single meal. Interestingly enough, stay elevated for almost a week. That this really reiterated another concept. Sure, gluten does this leaky gut to everybody, but in people with celiac disease and type 1 diabetes, and we have some data in MS as well, this leakiness is much more sustained compared to normal people. Normal people will go up and down, but in terms of, people with celiac disease will go up and will stay up for almost a week. The folks that they got gluten plus this zonulin inhibitor had no leakiness to the gut, and consequently, compared to the ones that got gluten alone, they had this amount of symptoms in blue here, that we're talking about GI symptoms in general, they had almost 60% less symptoms. And now, this is the summary of many trials. There are 3 different trials, again, in which we look at placebo, i.e. gluten alone, or gluten plus the zonulin inhibitor in blue, and you see how all the symptoms are abated in any kind of trials that they went through. I'm going to finish with this, that I think that is quite interesting. This is a brand new field, guys, just came along. This controversial question about the microbiome, the leaky gut, and disease status, obesity, non-alcoholic fatty liver disease, and diabetes. So, what is this all about? What's going on? The overall rationale for these studies is that a leaky gut is considered to be associated with inflammation tone that can lead to obesity, fatty liver, and eventually type 1 diabetes. Very bold proposition, working hypothesis. Now, I want you to take a look at these numbers, because we're talking about in the last 2 years. There was nothing in the literature before 2 years ago. We start to see this coming. And again, these are not the quote-unquote wackos that publish this stuff. These are, the ones that were considered to be the conservative folks. So gut microbiota, intestinal permeability, obesity-induced inflammation, liver injury. Very interesting paper that, again, link all this phenomenon together. Intestinal permeability parameters in obese patients are correlated with metabolic syndrome risk factors, i.e. type 2 diabetes. Again, this published in March 2012. Nutrition, intestinal permeability, and blood ethanol levels are altered in patients with non-alcoholic fatty liver disease, 2012 again. And this was one of the last one that was published. Circulating zonulin and marked intestinal permeability is increased in association with obesity-associated insulin resistance. So, in other words, it looks like that now we are accumulating data, these are human data, in which a breached intestinal barrier can lead to the uncontrolled passage of substances, mainly bacterial components, that will eventually find as a first station the liver, because all the blood through the mesenteric circulation will first stop will be the liver. And when this bacterial component got there, they can create the inflammation that characterize, this non-alcoholic fatty liver disease, and with that, the metabolic consequences that we discuss, i.e., type 2 diabetes. Now, I don't want to leave you with the misconception that now we have the solution of obesity, type 2 diabetes, because this is only part of it. Lifestyle is important. If you eat 5,000 calories or behave like this, of course you will be obese. But there is now the possibility of opening a new paradigm in which even if you have a regular lifestyle, if you, for example, have SIBO and you have genetically skewed toward this metabolic imbalance, you may eventually develop type 2 diabetes and obesity just simply because of this dysbiosis. There are now studies from WashU in which they found a specific microbiota composition that make you fat. And they show this by taking this, enterotype kind of microbiota and transplanted in different animals and make lean animals fat. And again, stay tuned, because this is an extremely dynamic field in which now we start to see unbelievable stuff. The most skeptical individual that leaky gut exists really start to rethink about it when the human genome and therefore epigenetic came into the picture, because now we start to see that many autoimmune diseases, they have as genetic component genes that are mutated that control the permeability of the intestine. So all this to say, guys, that we are at the verge of a revolution, if you wish, that was totally unintended. As far as I'm concerned, because I told you how the story started. And this is a typical example of how science advances, and the fact that it takes a village to do that, including the fact that you have to have an open mind and be ready to say, I was wrong. I want to finish by saying that I don't want to leave you with the misconception that this is a single-man operation. I didn't do that. I made the mistakes. The one that fixed the mistakes are these folks here. These are the people that are dedicated to science for the good of knowledge. These are people that work really extremely hard to try to achieve the goal that we signed for, i.e. to increase the quality of life of the people that come to us. Thank you so much, guys, for being here today.
You've just listened to Dr. Alessio Fasano's second lecture and his research results on Zonulin, intestinal permeability and immune-mediated disorders, differentiating between fact and fantasy. Cell Science Systems has several assays relevant to this lecture series, the first being markers which determine genetic predisposition for celiac disease. This includes the HLA-DQ2 and DQ8 genes. Also available are various antibody markers, such as tissue transglutaminase, TTG, and deaminated gliadin peptide, DGP. As well, ASCA, anti-Saccharomyces cerevisiae antibody, found primarily in inflammatory bowel disease patients with Crohn's disease. Additionally, cellular analysis for gluten and other food sensitivities using the ALCAT methodology is available. These assays are available to providers in various single and multiple assay configurations. To inquire for additional literature or research, you can contact the lab at info@alcat.com.